Guys, okay, 9.2 is slope fields. This is one of those sections which is a little difficult to do by video, but I think I've got a pretty good trajectory on how to do this. It's much more of a feeling your way through kind of section than pure method that we've some of the sections in the past have been. But we'll just go ahead and forge through bravely, and if y'all have any questions, this will be one of those ones that I'll just require you to shoot me questions by email and make sure that you understand. Slope fields were not a part of the curriculum when I was in calculus in high school and college. They became part of the AP Calc curriculum in the mid-90s. And therefore I actually was unfamiliar with them when I actually came to teaching calculus, and I actually had to learn them myself. They're not really all that difficult. It just takes a little bit of working with them just to become comfortable with them, just like anything else. Now remember that when we were dealing with derivatives, we dealt with a derivative of, say, x squared, and it was 2x, right? But if you dealt with the integral of 2x, you had x squared plus c, right? There was one derivative of x squared, but there was an infinite number of antiderivatives of 2x. Remember, the integral, or the antiderivative of 2x, is equal to x squared plus c. It describes a family of curves because there's that possibility of there being any constant sitting out there, hence why we put the plus c. Now what slope fields do is they take the logic of the integral and they basically sort of amplify it, okay? So here's what we're going to do. Let's go ahead and look at this. Now, here I've actually already gone ahead and used this slope field generator to show you what a slope field looks like for 2x, okay? So what was the integrand is now the differential equation, okay? And x plus x is 2x. I think it's a little bit of a old school thing, so it didn't allow me to put 2x, but x plus x is the same thing. Now notice that if I wanted to basically at any point follow the lines on this slope field, I can go ahead and do that. Sorry, it's a touchpad mouse. It's a little bit imprecise. But we see the fact that that could be a solution depending on what c value was. And that could be a solution right there. That could be one solution. And, all the way down here, and that could be a solution to it. So it really does depend on exactly, it does depend on an initial condition. But what the slope field does is instead of just giving us something plain like this, it gives us a representation. Dy dx is equal to 2x. It gives us a representation of any and all functions that could have this as a derivative. Or more to the point, it shows us what the directionality of the derivative would be at any point in the plane. Okay? Well, the great thing is that it does it for this, but it also does it for stuff that, is a little less integrable, like x plus y. Now this one was solely dependent upon the x variable. Now if we go back, x plus y is going to be, I'll go and clear that. X plus y is going to be a little bit different. And notice that the slope at any point in the field is now dependent upon both x and y. And so, if we wanted to actually draw if we actually wanted to use, let's say, that point right there as the initial condition, we could go ahead and mark out, just sort of sketch what the solution would be given that condition. Now, of course, if we have this as the initial condition down here, the shape of that graph is going to look awfully different. It's going to look something more like that, okay? So what we have here is, like I said, it amplifies it because it opens up greater possibilities for us to actually look at in terms of using the derivative to describe a family of curves, okay? Well, that's all well and good, but let's go ahead and let's look at what it would look like to actually construct one of these on our own. Because oftentimes on an AP exam, you are asked to construct one. Okay, and you'll be given something like this. Well, let's go ahead and let's say that we are given dy dx is equal to negative x over y. Okay, now here's the thing. Whenever you do something like this, what you want to do is you want to figure out the easy ones to do first. Obviously, everywhere where x is equal to 0, okay, as long as y is not also equal to 0, if x is equal to 0, the derivative is 0. So here, x is equal to 0, so you have okay, well, and we could actually set up a chart. I mean, if we wanted to, it, really wouldn't be that hard. You say, well, x and y, and then negative x over y, and we could actually construct a little chart. And let's say we have, where x is equal to 1. Okay, well, x is equal to 1 and y is equal to negative 2. That would be negative 1 over negative 2, or 1/2. If x is equal to 1 and y is equal to negative 1, that would be equal to 1. If x is equal to 1 and y is equal to 0, that's undefined, okay? If x is equal to 1 and y is equal to 1, that's going to be negative 1. If x is equal to 1 and y is equal to 2, that's going to be negative 1/2. Well, we can go ahead and plot those. So obviously, the easiest one to do is 1, negative 1, and we have a slope of 1. Okay. At 1, negative 2, we have a slope of 1/2, so it's just a little bit flatter. Here at 1, 1, we have a slope of negative 1, and here at negative 1/2. Okay, well, let's go ahead and do a similar chart for x is equal to negative 1. Okay, well, if x is equal to negative 1 and y is equal to negative 2, then I get negative 1/2. If x is equal to negative 1 and y is equal to negative 1, I'm going to get negative 1. If x is equal to negative 1 and y is equal to 0, I'm going to get undefined. Okay? If I have negative 1 and 1, that's going to be positive 1. If I have negative 1 and positive 2, that's going to be 1/2. Well, let's go ahead and look at negative 1, negative 1. Okay? I get a negative 1 slope. And if I have negative 1, positive 1, I have a positive 1 slope. And this is going to be half and negative 1/2. Okay, now the question is, what happens here and here? Well, an undefined slope, if you remember, is straight up and down. So we have actually taken those, let's see, 15 points, and we've actually constructed the slope field based upon that differential equation right there. Okay, well, what happens at 0, 0? Well, 0, 0 is, indeterminate, so we just kind of leave that one blank. Let's go ahead and go back to the slope field generator, and let's actually do this one, okay? Let's look at negative x divided by y. Do you notice anything? Well, I notice that if I want to use an initial condition, say right about here, I would just follow this. Oh my gosh, that looks like the curves that are being generated here are circles. Now, of course, my approximation is bad. Like I said, I'm using a touchpad mouse, and it's a little bit difficult to do. That would be the solution, because basically what you have to do is you need to start at the point that you're given and just follow the flow. It's almost like if you've been to the rodeo or a sporting event and all the crowds are going through, you're sort of forced to go and walk in the same direction as the crowd, okay? So think of the directionary lines in a slope field as just the crowd moving through a stadium at either, you know, the Houston Livestock Show and Rodeo or a Texans game or something like that, okay? And you have to follow the flow of traffic. That's all you've done here. You followed the flow of traffic as you've gone around, and it has made into a circle. Okay, well, the next question that then should spring to mind is, well, how do I actually get from here to a circle? Well, I'm so glad you asked. Let's go ahead and take a look at that. If I have dy dx is equal to negative x over y, I notice that that is a derivative, and basically that looks kind of like a derivative that I could have taken implicitly. Okay? Basically, all of the differential equations that you are likely to see will look like the end product of you having taken the derivative implicitly, especially if there's both an x and a y involved, okay? So here's what we're going to do. We're going to undo implicit differentiation. And in order to do that, we need to remember that dy dx is in fact a ratio, okay? So if I have one ratio equal to another ratio, this is a proportion. In order to solve a proportion, we can go ahead and cross multiply. Okay, well, let's go ahead and let's integrate both sides. Now, if I integrate both sides, I don't actually have to put a c value on both sides. I can just put it on one side, right? Because if I put it on both sides, I could then just subtract one constant from one side over to the other side and combine them, and really it just winds up being one constant. Well, at that point, we can go ahead and add the x squared to the right-hand side. And then we can multiply through by 2. And I guess that's a different constant, so we could put c sub 2. What does that look like? Well, it looks like the standard form of the equation of a circle, if you remember conics, right? Remember that a circle is just a specific case of an ellipse. Now, this is what is called a separable differential equation. And we'll go ahead and get to that in a later section. But I just kind of wanted to tie it in since we were exploring the multiple aspects of that particular differential equation. Some of them you actually can solve. Now, some of them you can't. Okay, but some of them you can solve, and this is one of them. The easiest ones to solve are separable differential equations, which is, you know, fancy terminology for ones that you can separate all the x's and dx's together and all the y's and dy's. If you can collect the x's with the dx and all the y's with the dy, it should be very straightforward in terms of being able to integrate and actually get back to what's called a general solution of a differential equation. Okay? Now, that sort of is a nice sort of intro into kind of the not only slope fields and how to construct one and how to reason through one and kind of where they come from, but also where we're going in terms of actually solving those differential equations when the need arises. Okay. In the next video, we'll get into a few more. Examples of dealing with slope fields and solving a couple problems dealing specifically with those.